Please, the break is over. Take your seat. We are going to continue this morning sessions. Now our speaker is going to be Giulia Gubitosi, and she's going to tell us about the interplay between a space-time curvature, a speed of light, and quantum deformations of relativistic symmetries. So please, Giulia, take the floor.
Thank you very much for the introduction. Thank you everyone for being here despite the weather. Well, or because of the weather, you cannot go anywhere else. So you're here. So in this talk, it is not going to be too technical. What I'm going to do is to show, so we have heard in many talks that we want to work in a framework that keeps relativistic invariance. Well, we have the Lorentz breaking framework as well, but we have heard a lot about this Lorentz, about this deformed special relativity story. And I want to give a bit of a sense of how constrained our models are if we really want to impose this this principle, the principle of relativity. We are going to see that we do not have many things we can do. There are many ingredients in our theory, but with a limited possibility for variation. So I will start. Well, okay. These are some references where you can get into the technical details in case you are interested, and I will provide a few more references during the talk. In particular, this here is coming out hopefully next week, and is going to be a bit of a overview of the topic. So my talk is based a bit on that. Okay, so we start from special relativity, of course, and we want to know what are the laws of inertial of transformation between inertial observers, and these transformations are given by the Poincare symmetries. We all know that. And so we have in 3+1 dimensions, we have 10 generators of transformations, namely time translations, spatial translations, boosts, and rotations. And we can describe the properties of our of these symmetries via the Poincare algebra. So we are just giving the commutators between all the generators. This is a Lie algebra, meaning that, for example, only linear, that we can modify the definition of our transformations, but only via linear combinations of the generators. And what is interesting is that from this algebra we get, well, the Casimir, which is an object that is invariant under the algebra. In this case, it takes the famous special relativistic forms, and this usually gives us the dispersion relation, for example, for point particles. It is important that it is an invariant because we want the dispersion relation to be an invariant of our theory. Otherwise, we would see a dispersion relation in one frame, another one in another frame, and we would not be in a relativistic theory. So this is why it needs to be a Casimir of this algebra. Now we can start thinking about what kind of modifications we can perform in order to go to a different relativistic framework. And well, there is one case that we actually know about, which is classical deformations of symmetries. One example, if we want to add the cosmological constant to our theory, then we go from the Poincare relativity, let me call it that way, to the de Sitter relativity, which is just the relativity that holds in a de Sitter, well, or anti-de Sitter space-time, depending on the sign of the cosmological constant. What is important here is that once you do this deformation, you are adding a scale. In this case, you are adding the lambda, so this is a squared distance scale. And this allows you to modify these commutators in a way that is dimension that makes sense from a dimensional analysis point of view. This also tells you when you should change your relativistic model from the Poincare relativity to the de Sitter relativity, which is when you are at length scales comparable to the length scale that you have introduced in your model. So in this case, if we think about lambda as a very infrared length scales, this will be relevant at large distance scales. So for example, in cosmology. So you can just go from Poincaré to, well, here I always put, I remember that this is also anti-de Sitter, but I will just say de Sitter and that's it. It's easier. So you can go from Poincaré, add a scale and go to anti-de Sitter. This is just very standard. And what happens, so we can see how the commutators are modified. So this was what we had before. And you see that we can change, because we have this scale, we are allowed to change the commutator between translations in this way. And in particular, and this is a famous feature of spaces with curvature, that translations do no longer commute. This is what signals that we are in a curved space-time. Of course, because we are changing the commutators, then also the Casimir is different. And we can add this term here. This term, so I said the Casimir is a distortion relation. This extra term is just the one that encodes energy redshift in the Sitter space-time. You can work it out. I mean, from here is a bit abstract, but that's it. It tells you about the energy redshift. Okay, so we saw one way to modify Poincaré relativity. Another way that is a bit less trivial is instead of doing classical deformations. What is important is that this is a Lie algebra and this is a Lie algebra. I'm not changing the theoretical framework. It's still a Lie algebra. When I go to quantum deformations of special relativity, again, how can I do it? I add a new scale. In this scale is, in this case, the scale I call it Kappa, and it is an energy scale. So in general, we will expect that these deformations will be relevant at energy scales that are comparable to Kappa. And this is just, I can look at it just as another direction of deformation. So instead of going to a classical deformation, I go to a quantum deformation. And well, there are many ways you can do this. Here, I will focus on the framework of algebras. So when you want to do a quantum deformation, you need to go beyond the Lie algebra structure. So you need to invent something else. One way to do it that is very well studied, so it provides a framework that is, I would say, quite well understood, is this one of the algebras. Again, I'm not going to go into the detail of what they are. I will say just a few things in a bit. So again, so one important feature, for example, of the algebra is that not only linear redefinitions of the generators are allowed, but also non-linear redefinitions. And this in particular, so for those of you who are not experts in this, you might have heard in the past days that we were fighting with each other about whether if we do a nonlinear redefinition of the translation generators, we go to a new physical theory or not. I mean, in the language of the algebras, this is just about going to a different basis of the algebra, and then there are questions, I would say, still open questions in current research about whether this new basis should be regarded as a new physical model or not. Here, I'm not going to go into that. I'm just going to use one specific basis that is known as Bicross product basis, but I could have used another one. So in this case, I go from, again, I take my Lie algebra of Poincaré, and I introduce the scale. Now you see that the kind of deformation that I get is a bit more, it looks a bit uglier than what I had in the De Sitter case. So actually everything remains the same at the level of the commutators, apart from the commutator between the boost and the translation. And this is the kind of deformation that we get. Of course, when kappa goes to 0, we recover what we had before. And also the Casimir, which is related to the dispersion relation, gets deformed in this way. And you see, in the end, just in the same way as the deformed Casimir of the Sitter algebra was encoding the energy redshift, this deformed Casimir here somehow encodes the energy-dependent velocity for massless particles, so the time delays that we all think about in this room. And it just comes from asking that this object, again, needs to be invariant under the new algebra of symmetries, because we want that the dispersion relation is not dependent on which observer is looking at it. Otherwise, we would be introducing a preferred frame again. So because we are in a hot algebra and we have this possibility of doing nonlinear redefinitions and so on, we need to add some extra structures to the algebra. So we cannot just give the commutators. And this is an important feature. So in the Lie algebra, if I take one of the generators, these generators act with the Leibniz rule, basically on multi-particle states or on products of functions. You can look at it in different ways. This law of action on multi-particle states needs to be modified as well, because if I took the standard one, it would not be covariant under these deformed generators. And so I am forced to introduce a deformed action on multi-particle states, or I can look at this as a deformed law of composition of energy and momenta. So this is why when we go to deformed special relativity, we often talk about not only the modified dispersion relation, but also about the deformed interactions, because it is just, again, a matter of consistency. If we want to keep relativistic consistency, we need to also include this kind of deformation. And in particular, you see here that what is deformed is the action of time translations and boosts. This could vary depending on the basis of the algebra that I'm considering. This is one option, but it's enough to show my point. So as I mentioned, so until now I gave you two different scenarios, one of a classical deformation and one of a quantum deformation, and I have shown you how different they are. But in fact, it turns out that they are not so different, at least in some respects. And in fact, I can look at them as two dual pictures. So here on the left, I have the de Sitter spacetime picture, which is the de Sitter relativity story, the classical deformation that I talked about at the beginning. On this other hand, I have this quantum deformation, which I can look at as introducing a deformed geometry on the momentum space. This is a long story. I'm not going to talk about it here. You can see papers or ask me later. But the momentum space of this quantum deformed algebra turns out to have curvature, and in particular turns out to have de Sitter geometry. So on one hand, I have de Sitter geometry on space-time. On the other hand, I have de Sitter geometry on the momentum space. If I write the relations of the algebra also with the space-time coordinates in terms of these coefficients here, so they're just related to lambda and kappa in this easy way, you see that the structure is exactly the same if I exchange x and p. So for example, here I have n p0 is p1, and here I have n x0 is x1. And it is, so you might have heard in previous talks about this dual redshift, dual lensing. So in what sense, what does it mean dual? It is in this sense. So it is exchanging the role of space-time and of momentum space. And for example, in the Sitter space-time, the Casimir of the algebra, so the dispersion relation, so the dispersion relation comes from the Casimir of the algebra of n p0 p1. This is in 1 + 1 dimension here. In the momentum space story, the dispersion relation comes from the Casimir of n p0 p1. So you can really look at these things in a very similar way, and I think it is very helpful to understand what is going on. Here is just another few examples. So the metric, you see, it is very similar because it's just the Sitter metric. What would be the word line in the Sitter space-time becomes the dispersion relation in the Sitter momentum space, and vice versa. And I can look at the generators of translations in the Sitter space-time as the so-called Kappa-Minkowski coordinates in the Sitter momentum space models. So this is just a general feature about algebras where non-commutativity on one side, so on space-time or momentum space, induces curvature on the other side, and vice versa. Okay, so we have talked about classical and quantum deformation separately. Of course, because I'm drawing these funny figures, it means clearly that I want to join the lines. So we can actually have pictures in which we are both classically and quantum deforming our special relativistic model. This kind of deformed algebra, of course, will be relevant when we are both at high energies and large distance scales. So when we are doing cosmology or when we are looking at astrophysical distances. Again, this is an example. This Kappa deformation that I'm talking to is one example how you can do the deformation. You could think about other models, but I think it is just nice to look at. I mean, these have been worked out more in detail than other models, so this is why I'm talking about these ones. So what is interesting here is that what you get in this corner of your diagram is not just the trivial sum of the effects that you get because of the classical deformation and of the quantum deformation, but you actually get new effects that only appear when both the deformations are present. So you cannot really build your intuition about what is going on here by just looking naively at these two corners of the diagram. You really need to work it out. So let's see some of the non-trivial things that happen. Again, this is the starting point, and now I want to do a lambda and the kappa deformation. First thing that I notice is that if I look at the translation sector of the theory, so you see that in special relativity, the commutator between translations is just 0. It becomes non-zero because of the curvature lambda. This we have seen already in the Sitter relativity. But then it gets a lot of extra correction terms. Sorry, so here eta is basically lambda. I just copied the formula from a different paper. So you see that these formulas get much more complicated. And in particular, you see that they do not look very symmetric among themselves. So you start worrying, what is happening here to rotational invariance? Until now, we were only looking at boosts and translation. And rotational invariance is something we really are afraid of touching. And here we start worrying. And in fact, it turns out that, okay, we should worry, but not so much. Because so once you add the combined effect of rotation, of curvature and of quantum deformation, the algebra of rotation is deformed. We still don't know what would be observable effects of these, but what I want to say is that it is not a breakdown of the symmetries, just in the same way as deforming the boosts when we do the quantum deformation is not that we are breaking Lorentz invariance, we are deforming it. And here it's happening just the same, but in the rotation sector. So you see that you have one preferred rotation generator. And this is an effect that, as you can see, only appears when you have eta over kappa. So you only have it when the two parameters appear together. There are other effects that only appear when the two parameters are together. Here I'm just going to briefly look at what we are more familiar with, and in particular in the 1+1 case, because the 3+1 still needs to be worked out. So if you look at the dispersion relation at the world lengths of particles living in this relativistic theory here, you get effects on the redshift and on the particle world length. So for the redshift, the first term is the energy redshift that you would get in the Sitter spacetime. So it's just the usual one. And then you see that you have a correction term, this 1/2, that only depends on L. Well, L is 1 over kappa, as I showed before. So then you have one term that only depends on the quantum deformation. But then you have a term that depends both on L and on H. So this only appears when you have both effects. And a similar thing for the for the word line. You have the quantum correction alone. Then you would have a bit that is only the one due to the fact that the particle is propagating in a curved spacetime, but then you have an effect that is L times H, so it is a mixed effect. And these have, of course, consequences if you look at time delays. So this is a delta t, basically. And this would be the part that you would have only in the quantum deformation case, but then it gets corrected with the curvature. And the same thing for the redshift. This could be related to, for example, the model that Giacomo was talking about the other day, but it's not one of the cases where you have effects that only appear. So it's not one of the cases where you only have a time delay when there is curvature. Here you might have a time delay even without the curvature, but then you have mixed terms, just to, if someone was wondering what the connection was. Okay, so now we have seen two ways of deforming special relativity. And in the last maybe 8 minutes, I guess I'm going to look at yet another direction in which we can deform. And namely, it is by contractions. So you know that if you take the speed of light to infinity in special relativity, you just go to a Galilei theory, which is a fully relativistic theory. Again, it's just a deformation of special relativity, but of a contraction kind. Or on the other hand, you can look at the Poincaré algebra as a deformation of the Galilei algebra. Depends on which direction you want to go to. So we are all used to think about Galilean theories, but there is also the possibility of doing another kind of contraction that would bring you to what is known as Carroll contraction. So this was first uncovered in these very nice papers from the 60s, which I recommend reading just because they are very, very beautiful to read, even though you might not be interested, especially in Carroll relativity. Anyways, recently it has been this kind of contraction has been studied a bit more in several contexts, and it seems that it might be relevant in a strong gravity regime close to black holes and in primordial universe. Studies are still ongoing, but it seems that it might be worth looking at together with the Galilei more famous contraction. So of course you can do these contractions also in presence of curvature. So you can send the speed of light to infinity when you are in the theta relativity, and to 0 when you are in, and go also in the Carroll direction. And well, here I'm just going to show you quickly how you do it. So for the Galilei case, you need to know that well, you need to look at you need to reintroduce the C parameter that was set to 1 until now into the commutators of your algebra, then take the C to infinity limit. And the important features is that the boosts commute, because we know that in the Newtonian world, this is the most important feature in the Newtonian world, that tells us that space and time are not mixing any longer, which is what happens in special relativity. And then we see that the effects of the curvature that we had for the translation sector disappear in this limit. So this is also an interesting interplay between curvature deformations and the speed of light contractions. And also you can do this for the Casimir. In the Carroll case, you can do something very similar. And again, we see that also the Carroll case is a non-relativistic model. Well, non-relativistic meaning non-special relativistic, but it is relativistic in the sense that we do not have preferred frames. And you see this because the boost commutator is 0. What is interesting to see is that because this commutator becomes 0 here, you know that in Galilei, in the Newtonian physics, we have absolute space. And you can just read it off from here. In the Carroll case, because you have the commutator with P0, that is 0, means that you have an absolute time. So they are kind of similar, but in one case you have absolute space, in the other absolute time. Well, and this is just wanted to show you how things are. So in both limits, you get this zero commutator between the boosts that gives you this that tells you that you are not mixing space and time any longer. You have absolute time, absolute space, depending on what contraction you are considering, and the Galilean limit erases the effect of curvature that you would have in the full de Sitter algebra. Then the question is, can I do similar things when I also have the quantum deformation? And the answer, of course, is yes. So I go from this picture to the full picture. So here every corner is a different relativistic model. So we have been building lines along the top. And each of these, it has very nice properties, and you can study what happens in any combination of the directions of deformation that I have been talking about. Of course, the easiest way to move around here is to start from here, where everything. So this would be the Kappa deformation of the Sitter would be the place where you have all the deformation at play at the same time, and then just do contractions to go to the other vertices. And well, I'm not going to go into many details here because I don't think there is much. I mean, one can look at it, but in general, I think what is relevant is that, for example, when you put this quantum deformation and you go to the Galilei contraction, the most striking thing I would say is that you lose the absolute time feature of Galilei models. So you cannot separately look at space and time as we are used to do in Newtonian physics. This does not happen in the Carroll contraction. So here you still get your absolute space. So you are happy. And well, this is just the final slide. And is a table showing how the different scales enter in the different for the different deformations that you can consider. Something interesting is that, for example, we were worried about the fate of isotropy, of rotational invariance in the Kappa and the Kappa deformed curved case. Actually, rotational invariance is restored in the Carrollian limit. Doesn't happen in the Galilean limit, unfortunately. We see that we lose this property of having commuting boosts in the Galilei limit because of interplay between lambda and kappa, exactly. So this is another non-trivial effect of this interplay. Doesn't happen in the Carroll case. I mentioned already that we lose absoluteness of time, but we can retain absoluteness of space in the Carroll case. Well, and that's it. Thank you.
Thank you very much. I have myself a question.
Yes.
Well, I mean, the limit for special relativity to Galilean relativity, as you mentioned, is very easy to find that participate to infinite or
yes.
infinite speeds, which are much smaller than.
Yes.
Do you have any intuition? How do you go from special relativity to Carroll?
Yes. So
the limit that works there, and how can one imagine what's happening?
Exactly. So one way to look at it is to think about large space intervals. And yeah, it's not easy. So more formally, in the Galilei case, you have that your Poincare algebra is invariant under this parity transformation. You can rescale your generators, these two generators by C, and send it to 0, and you get the Galilei case. In the Carroll, you exploit the time reversal invariance of the story. I mean, it is still a case where you're separating, at least in the flat case, you're separating space and time. In one case, you would look at large velocities and large space intervals, and in the other case, small velocities and small space. Yeah, it's a bit hard to say it in general, because so usually we talk about the Carroll limit as the ultra-relativistic limit, no? So it is when you would send the speed of light to 0. So any other speed is infinite compared to. So this is maybe the most easy way to look at it. And in this case, for example, it is hard to you cannot describe motion because you just have no way to have a velocity. Maybe this helps more. Yeah, maybe this is the way to answer.
Thank you very much.
Sure. You want to go? Everyone's tired. Yes, but I don't hear you.
Do we have another microphone?
Just wanted to ask if in the four-dimensional two-de-Sitter algebra, are you sure that there is no redefinition of the generators such that you can obtain isotropy in rotation?
No, within this framework, no. You can change what looks like the preferred direction, but you cannot remove it. It's just a consistency relation of the structure of the algebra.
So there is not a basis which is isotropy.
No, there aren't.
They're not.
No.
Okay, thank you. Any other question or comment? Oh, yeah.
What is the dispersion relation of particles when you have these both classical and quantum deformations?
So in 1+1 is this one. Where is it? Is this one here for a massless particle? So this is just energy, and this is spatial momentum. No?
X0. What does it mean to have a dispersion relation depending on X0?
It's energy redshift. I mean, this is what you have also in the Sitter, no? This term here, 1 minus h, it's the A factor, the scale factor. It's just that I write it in this way, but it's energy redshift, and you can correct it with your deformation, your quantum deformation, but it's just energy redshift.
Mm-hmm.
Okay, if there are no more questions, let's thank Giulia again.
Thank you.
On our next speaker is Michele Arzano. And he's going to tell us about decoherence and discrete symmetries in deformed relativistic kinematics.
Thank you.
Okay, so Michele, take the floor.
Yes, so during these days of the conference, when people were talking about deformed relativistic kinematics, the main ingredient of these models that was used to look for phenomenological signatures of these deformations was the deformed dispatch relation. Okay, the dispatch relation between energy and momentum. The punchline of my talk today would be that there are other features of these deformed relativistic kinematics models which lead to possible observation which concern other phenomena than, for example, time delays that have been widely discussed in this conference. And these phenomena concern fundamental decoherence and a deviation from ordinary discrete symmetries. So the whole story that I will tell today starts back in 1983, what I would call the prehistory of quantum gravity phenomenology. In this paper, Ellis, Sagalin, Nanopoulos, and Srebnitsky basically proposed to search for fundamental decoherence in quantum mechanics using long baseline neutron interferometry and systems of observation in systems of neutral counts. What was their motivation? Their motivation was the result by Hawking, published a few years earlier, that maybe in the quantum evolution of black holes, we can have a pure state which evolves into a mixed state, thus violating some of the basic axioms of quantum mechanics. Let us look at this more in detail. So in ordinary quantum evolution, if you start with a density matrix rho initial, we have a unitary operator which describes the time evolution. So the final density matrix at some time would be given by this action of the evolution operator on the density matrix. Now, if the initial state is a pure state, so the trace of the square of the density matrix is 1, then this property is preserved, okay, by the action of a unitary evolution operator. Now, if indeed black hole quantum radiance, black hole evaporation suggests that we can have the possibility of evolving a pure state into a mixed state, then we have to replace this unitary evolution operator with something that Hawking called superscattering operator, such that we can allow the final density matrix to have the trace of its square less than 1. Okay, so the idea of Ellis et al. In this paper that I showed in the previous slide was to explore the phenomenology behind this possible non-unitary evolution. And to do so, they just studied a infinitesimal version of this evolution, where basically instead of having the ordinary von Neumann evolution term for a density matrix, you would replace by a generic operator H slash, okay, which is which describes this non-unitary evolution. Let us look more in detail at this at the form of this H slash. This was done by Banks, Peskin, and Susskind in a year later. So basically, what they did, they assumed that this more general quantum evolution preserves hermiticity and the trace of the density matrix, two fundamental properties. And by imposing these two requirements, what they obtained for the general form of this H slash operator was this thing here. So here we have an evolution equation for the density matrix, which contains the ordinary von Neumann term, okay, so the commutator of the density matrix with the Hamiltonian, plus this additional term, which leads to the potential evolution of pure states into mixed states. And here we have basically a complete set of orthonormal matrices, Q and Hermitian, and H alpha beta is a Hermitian matrix of constants. Okay, so this is known as the Lindblad equation. These guys rediscovered it because this equation was already known to people who were doing evolution, quantum evolution in open quantum systems. Okay, so when you have a quantum system which interacts with an environment. The new thing here, the new theoretical aspect is that you expect some kind of evolution of this type to emerge at the fundamental level, you know, so to be fundamental, not because you have an environment. So the question of whether this modification of quantum evolution is physically viable or can be obtained from a more fundamental theory or quantum gravity model has been debated since these, you know, the early 80s. What I will show today is that some of the models of deformed relativistic kinematics that have been widely discussed during this conference actually can realize this type of evolution. And the main ingredient of these models is that we have a momentum space which is no longer a vector space, but is a Lie group, non-abelian Lie group. Okay, and the curvature of the manifold of this momentum Lie group is set by a UV energy scale. Okay, which we will denote throughout as Kappa, with Kappa. This non-abelianness of momentum space leads to a notion of deformation of translation generators, as we will see in detail. And essentially, this group manifold structure of momentum space affects the some very basic notions in quantum theory, leading to potential fundamental decoherence and a deformation of discrete symmetries. Yes. I will have 2 more minutes then, right? Sure. And this was shown in these works by myself and in collaboration with Professor Kowalski-Glickman, who was here at the school, and Wojtek Wislicki at the Institute of Nuclear Physics in Warsaw. So let's get started with the real stuff. The model I will focus on was basically the model which has been discussed a lot in several talks in this conference, and Giulia just introduced some of the features of this model. This is the Kappa Poincare algebra. The formation of the Poincare algebra historically was introduced almost 30 years ago by this guy, some Polish mathematical physicist. At the time, it was fashionable to deform everything. The quantum groups were just introduced, and so the idea of these people was to use quantum group tools to deform relativistic symmetries, the algebra of relativistic symmetries, Poincare algebra. So in this model, the deformation parameter kappa introduces can be seen as a fundamental observer-independent energy scale, UV energy scale. We can think of it as a Planck scale, and this is as the basis of the idea of having. This was observed by Amelino Camella in well, 20 years ago now. And so the deformed kinematics associated to this model provides the prototypical example of a doubly special relativity model, okay? Where basically you think of some effective flat space-time limit of quantum gravity, where the Planck scale plays the role of a fundamental independent, observer-independent quantity. So let us look at briefly at what the Kappa deformation is. So the basic geometric picture is that you have a momentum space, which is a Lie group, as anticipated. This Lie group I denoted here with A and 3. We are in 3+1 dimensions. And you can think of it as essentially a subgroup of the 5-dimensional Lorentz group, SO41. Okay, you decompose the 5-dimensional Lorentz group in these 2 factors. You have the ordinary Lorentz group and this A and 3 Lie group. And this is very important because it ensures that this momentum Lie group manifold has a well-defined action of the Lorentz group, which ensures that you have a relativistic theory. You have an action of the Lorentz group on your momentum space. Okay. As a manifold, this group is given by half of the Sitter space. So, and I can write them. This is basically embedding coordinates on this submanifold of the Sitter space. Okay. The algebra associated with this group forms the so-called Kappa-Minkowski non-commutative space-time. okay, which has been discussed widely in this talk. Okay, so how do these structures affect quantum theory? Okay, in order to appreciate this, let me go back to some fundamental features of quantum field theory. So in quantum field theory, one particle states are elements of a Hilbert space which carries an irreducible representation of the Poincare group. So normally what you do, what you learn in textbooks, you just work with some cats labeled by momenta, okay? So the action of these are translation generators of your Poincare algebra, and these are eigenstates. These kappa cats are eigenstates of these generators, okay? They carry a momentum kappa mu, okay? This is the generator, this is the eigenvalue. Now, you can define a dual Hilbert space, which is a space spanned by bras, okay? And the theory of representation of the algebra tells you that you have an action of these guys, of these translation generators on these bras, which is given by the following. So this is minus the eigenvalue of the cat, okay, acting to the left. And this can be written in this way. You can just set, bring the eigenvalue on the other side and say, okay, instead of acting to the left on the bra, I'm acting to the right, not with p mu, but with another operator, which I call S of p mu, which is basically minus p mu, which I call the antipode, okay? If I have more than one particle, then my Hilbert space is a tensor product, and the way I act with these translation generators on the same tensor product is by the Leibniz rule, as Giulia recalled before. Okay, so first I act on the first and then act on the second, like with derivatives. And this can be encoded in some in an operator which I call delta of p mu, which I call the coproduct. Okay. So this is the way they look, as I said. Okay, so you can write this coproduct like this. So first act on the first and then act on the second, and this is the minus p mu I was telling you. So these are notions of algebra which are built in our everyday quantum theory. We don't really appreciate, but they are there. So quantum theory implies an algebra structure for my symmetries. And then the interesting thing is that these notions are enough to derive the action of translation generators on a generic operator. Let's take, for example, this density matrix for a pure state, okay? Or a projector, call it as you want, rho k. Then p mu, you act on this object by using first the coproduct, so the Leibniz rule, you share the action of p mu first on the first term and then on the second term, but the second term is a verb here, so I need to act with the antipode. So I obtain this action, okay, and this is nothing but the commutator, the adjoint action of an operator, in this case the translation generator, on a density matrix, another operator, okay. And I can write this, so this is familiar adjoint action, okay, which I don't add p mu on rho k. And I can write this in this fancy way, just to tell you that the basic principle is that in ordinary quantum theory, I have this antipode and this coproduct, which are kind of trivial, but as well I will show in the Kappa Poincare model, these are highly non-trivial. So what I'm going to do, I'm going to write this adjoint action of translation generators on the density matrix in this way, okay? So I have identity times the antipode and then combined with the coproduct, and then this circle operator here is basically telling you that I put the rho k between the two operators that I obtain. Okay, I will show you in detail later how this works out. So now, in the presence of deformation of symmetries, we have a generalization of these basic notions of quantum theory. How? Okay, now I imagine now the cats on my theory being labeled by momenta pi, which are elements of a non-abelian Lie group. So a translation generator will act on this cat, and the eigenvalue will be some coordinates of, which I call this p mu here, coordinates of this group element pi, okay? And the actual numbers, I call them pi of mu. Okay, is this clear? So this is the action of translation generators on cats which carry a momentum which is a Lie group element. Now, for the action on bras, what I have now is this coordinate functions, now we'll read the coordinates of the inverse group element, pi to the -1. And this is gonna be my antipode. And also action on multi-particle states will be non-trivial, because now if I think of the action on translation generator on this tensor product of two one-particle states labeled by group values, then this guy will read the coordinates of the product of these two group elements, okay, and this would be encoded in the coproduct, but the group is non-abelian, and so the total momentum carried by this object pi1 times pi2 would be different than the total momentum, say, carried by the object pi2 times pi1, okay, because the coordinates because these are two different group elements. Pi1 times pi2 is different than pi2 times pi1. The group is non-abelian, okay? So you have a non-abelian composition rule for momenta. How much time do I have? 11 only, okay. Okay, so that said, this shows that the non-abelian structural momentum space leads to coproducts and antipodes which are non-trivial, okay? And the point will be that the action of operators, the action of these guys on operators would be deformed accordingly. Let's see how. Let's look at now a specific translation generators associated to the Kappa Poincare algebra, okay? And I choose translation generators which give me embedding coordinates on this de Sitter momentum space. The coproducts and antipodes, a leading order in the deformation parameter kappa, are deformed in this way, okay? You see that here you have additional terms with respect to the ordinary Leibniz rule, and here you have not the trivial antipode, but you have some additional terms. This basis of Kappa Poincare is called classical because the action of the Lorentz sector on this generator translation is undeformed. So you have the standard Poincare algebra, the algebraic level, and you have undeformed mass shell condition, okay? So undeformed energy momentum dispersion relation. All the non-trivialities are here in the so-called co-algebra sector. Now, what you do, let us focus on time translations, okay? P0. For a non-interactive field theory, time evolution of density matrix is given simply by the adjoint action of the time translation generator on the density matrix. So if I recall this fancy way of writing the adjoint action, and now I use, sorry, here should be 0 here. This is equal, but should be 0. And I use the non-trivial coproduct antipode, which I have here. Okay, I introduce this non-trivial antipode and coproduct here. What I obtain is the following evolution equation for a density matrix. Okay, this looks like a Lindblad evolution equation with a term missing, right? I should have a p² rho term here. But this term is missing because the non-trivial antipode for P0 leads to a deformed notion of Hermitian adjoint. So in order for this guy to be Hermitian adjoint, I need this equation needs to be asymmetric in this sense. Okay. Of course, the question is, can I look at some phenomenological framework in which I could possibly put bounds on this kind of deformed evolution? Well, there have been, a long history of trying to put bounds on fundamental decoherence using neutral counts. Okay, and we have very high precision measurements done in Frascati by the Chloe and Chloe 2 experiment. So could we possibly put bounds on the kappa parameter using measurements of precision measurements of neutral counts? Or more relevant for this conference, can we look at the other experimental windows to put bounds on this kind of deformed evolution? For example, looking at the effects on neutrino oscillations for astrophysical neutrinos. There's some kind of very interesting recent reference here concerning the possibility of observing fundamental decoherence in neutrinos. So the second part of the talk, but I think I don't have much time to actually go through it in detail, will concern discrete symmetries. So do these new structures which I just described affect discrete symmetries like parity, charge conjugation, and time reversal? Well, Wald back in 1980 pointed out that if you have some quantum gravity-induced fundamental decoherence, this would clash with the fundamental assumption of the CPT theorem, and then you would have some form of CPT violation, okay? And there is a long and venerable literature of phenomenological searches for fundamental decoherence and violation of CPT using these neutral count systems. As I showed in this paper with Kowalski-Glickman, the non-trivial antibody which I just described for Kappa Poincare generators actually is fundamental in the definition of discrete symmetries in this context and lead to a deformed notion of CPT transformation, okay? Now, let us look at parity, for example. So the basic physical requirement that we want to have is that the total linear momentum of a particle and its parity image must be 0, okay? So if this is your physical requirement, then parity must act on this way, for example, on the generator of spatial translations. So parity will just, of pi, will just give you the antipode of pi. Now, if you do this for the generator of spatial translations, you should do it for all the generators of the Poincare group, otherwise you would not close the algebra, okay? And so requiring that in the limit kappa going to infinity you recover ordinary parity transformations leads to the following forms of parity acting on the generators of the Poincare algebra, okay? I just wrote here the leading order terms. So essentially, you take the antipode for spatial translations minus the antipode for the time translations, the trivial antipode for rotation generators and boosts. Okay. And in the limit kappa going to infinity, you actually obtain the ordinary action of parity on the generators of the Poincare algebra. You know, now time reversal can be defined in a similar fashion just by requiring that in the kappa going to infinity, time reversal flips the sign of generators of rotations while leaves unaffected the generators of boosts. Charge conjugation is a bit more subtle. I don't have time to go through it, but essentially at the end of the day, what comes into play here is the fact that antiparticle states are described by the dual Hilbert space of particle states, and the symmetry generators act on this dual space via the antipode, as I discussed before. And so, again, imposing the kappa infinity limit, you recover usually the ordinary charge conjugation. You get the following action of charge conjugation on the generators of the Poincare algebra. We can put everything together to obtain the following definition of deformed action of the CPT operator on the generators of the Poincare algebra. So the main message is that if you have a non-trivial antipode, so you don't have to deform the algebra, the energy momentum specialization, just a non-trivial antipode in your deformed kinematics. This will lead to the action of the CPT or operator to be deformed. Notice this is different than the idea of complete CPT violation discussed by Wald back in 1980. Now, at the phenomenological level, for example, you could look at this effect. If you have a deformed CPT map, you can show that this leads to different lifetimes for particles and antiparticles, as we showed in this paper with Kowalski-Glickman and Wislicki. So if you look at this, the particle lifetime, okay, here normally we have the lifetime is the same for the particle and the particle, and this is, you know, gamma is the inverse particle lifetime. Now in our case, the gamma factor, the Lorentz factor responsible for time dilation, is E over m for the particle, but for the antiparticle now it is not minus E, but is it's the minus the antipode. So instead of being in E over m, you have minus p squared over kappa times n. Okay, and so you have two decay probabilities, and you actually can put bounds on this using data from muon lifetime at LHC. And for example, you can obtain this bound. Okay, that kappa has to be bigger than about 10 to 14 GeV, and this done with the energies currently reachable at LHC, and with the future collider, we would reach up to 10 to 16 GeV. The question for this audience is, could we set better bounds, for example, using astrophysical observations? All right, so done basically. Let me just summarize. A large portion of quantum gravity phenomenology studies focuses on modification of the energy momentum dispersion relation. I just showed that there exists some model of Planck scale deformed kinematics which predict fundamental decoherence and deviations from ordinary CPT invariants. Okay, and the phenomenology associated with these effects is largely unexplored. Actually, it is unexplored basically. So this cost action provides a unique opportunity to take advantage of these new two windows on the quantum gravity world. Thank you.
Thank you very much, Michele. I do really appreciate that you come to predictions that, well, have been somehow constrained already. What would be the natural scale for this Kappa? So this limit that now you have there is...
the natural scale, you expect this to be a Planck scale effect.
Planck
so
scale.
Planck scale, yeah.
Okay.
So Planck energy.
So still we are far away.
Yes.
Okay, good. Any other question or comment?
Just curiosity, when you have two decay probabilities, how is it clear how you combine them to put this bound?
Mm-hmm.
Which one did you use? The deformed one?
Yeah, sure.
Is it not going to depend also on how frequently that channel? It's like they have two channels to decay in some sense, isn't it? Or
yeah.
So isn't it going to depend also on how frequently that channel is? So it could be somehow also, I mean, there is a bit of information missing, which is usual. I mean, I'm helped by the fact that everywhere in this formalism, I find these spots where we miss something.
Probably, yes.
That we would need to know what is the balance of the two channels of decay, if they are 50-50 or
right,
or if there is some reason why one of them is suppressed. Because this could be, if it was highly suppressed, the new one, of course, then the bound would be even weaker.
Yes.
Because, you know, effectively it would contribute. So this was just a question. If
yes, right.
Thank you very much. That was a very good point. Any other question or comment? Yes.
Hi, very nice. So you showed that with this you can get something that is almost the Lindblad evolution, but not quite. Wouldn't that mean that it breaks some of the assumptions that go into deriving the Lindblad equation?
No,
you might have conservation of probability or something like this.
Yes, so this is a very good question. Well, the point is that you have this almost Lindblad, because as I said, you have to think that here all ordinary notions, like for example, the notion of Hermitian adjoint, are deformed. Okay, so for example, when you take the Hermitian adjoint of this guy, if you had full Lindblad, then it would be gone. I mean, you would just get another equation just by taking the Hermitian adjoint. Okay, and likewise, for example, if you study the covariance of this equation under the action of Lorentz boost, you have to take into account the fact that boosts also are deformed, so their coproduct is deformed, and so on and so forth. So that's a very good question. I mean, one should double check that this guy doesn't do anything weird, like for example, you know, violation of probability conservation and so on and so forth. That's right. Yes, but you know, that must be checked carefully within the framework that you are, so that you know that you have deformed notions of basically everything. Okay, so being careful about that.
Yeah, maybe I can add a comment that the other thing that I can imagine it could break is complete positivity, but which is not necessarily a problem, I guess, because if you're considering that this is a fundamental thing and not an interaction with the environment, as long as it conserves the probability in the system itself, you don't have to worry about the environment. So.
Yes. Right.
Okay, thank you very much.
Thank you. So the difference in lifetimes between particle and antiparticle depend on the frame you are, because it depends on the momentum. No?
Yes.
So this doesn't break relativistic invariance. There is an observer which is both particles at rest, and this observer sees that the two particles decay have the same lifetime. But another observer wouldn't agree with that. That doesn't break relativistic invariant.
At first sight, it does seem to, but you still have to consider that you really are in a your boosts are weird in this case. So your notion of covariance is not the ordinary one. So
but you can distinguish rest from movement.
Yeah, but this should be defined by boost in the full theory, right? Which is not the ordinary one. So it's a interesting thing to investigate.
Okay, I think we should keep moving on because the session is going to be longer than foreseen, and therefore I would like to ask to thank again Michele.
Thank you.
And now our next speaker should be Narine Ghazaryan, but she is aphonic, and I understand that her husband is going to be her voice and present the slides. So please, Ara.
Thank you for giving this talk. Also, it is we are collaborators and we have worked together. But she, due to the weather, she has come and have problem with her voice. So, but this old slides presented by her, if I present in a little bit different ideology or different approach, please. Okay. So it's we will present general theory of transition radiation in quantum field theory, and then we'll go to transition radiation to neutrino goes to neutrino and photon, neutrino goes to neutrino photon with on the edge of magnetic field, and finally it is our last work. It is neutrino goes to directly to another neutrino electron positron pairs on the interface in a very dense matter and vacuum. So this guy is Giulia Gubitosi, who calculated and predicted transition radiation in the late 50s, 59 and 60. When he calculated transition radiation, and then divided by Planck constant, he got that something is wrong because energy is much less than you can assume. Then he calculated in quantum field theory in 60s, 1 year later, and then they match each other very nicely. So quantum field theory calculation and usual field theory calculation of the transition radiation gave same results. And I want to say that transition radiation, when, for instance, you have interface between two mediums, and then electrons passing from one medium to another medium, it is just probability. We are calculating the probability, and probability is Lorentz invariant quantity. So even this Poincare invariant is not hold, but Lorentz invariant is there. So this process is responsible only for because momentum perpendicular to the interface is not conserved. Yeah, momentum is not conserved when you go to one medium to another medium, but the full probability, when you calculate probability is Lorentz invariant. So then I want to say that a few more words that transition radiation was also observed in first time in my institute. So we work with the same floor, with same group, with him and I and Dr. Ghazaryan, and this is very simple guy, so absolutely not arrogant. And I want to say that for other radiation processes, Brest-Hardenburg and Cherenkov radiation, people got Nobel Prize, but not for transition radiation, unfortunately. He died in beginning of 90s, very early. So then I want to say that also transition radiation by charged particle by electron was observed in our institute. And when the observation, they got this transition radiation effect, people doubt that this is not Cherenkov radiation, it is not transition radiation, it is Bremsstrahlung. And the guy who was performing that experiment that put this plastic material, this a lot of Bibles under the press, they remove all the Bibles and put under the beam of the electron. They said, look, there is no any radiation. So it is not Bremsstrahlung, it is transition radiation, really transition radiation. So there's stories on that. Okay, let's go to technical data, how he calculated this in the quantum field theory. In quantum field theory, we calculate probability, this probability. And as usual, you have these all phase integrals and so on. You divide by 2e and volume of the things, and you have this thing is the matrix element and 4-dimensional integral. And it is as it's a usual expression, but when you go to the you do replace by this exponential by delta functions, it turns that only you have 3 delta functions. The perpendicular momentum, energy, but not the direction of the perpendicular to the interface. Because perpendicular to interface, it is just, you have to do just manually. And manually doing, you are getting these things. So this matrix element in first medium, matrix element in second medium, and impulses and these impulses in the first medium and second medium. So if there is a, for instance, there is the same medium, okay, vacuum, or N1 is equal to N2, something like that, this will be exactly equal to this part, and effect will disappear. So nothing is wrong, everything is okay. And in this case, you have V, this is the volume, and then you have S, just square, and then the time, and then divided by each one, you are getting the velocity of the particle in the z direction. So in neutrino case, of course, it's almost 1. So again, it is technically, it's very simple. It's probability is just usual things, but with some unusual form, that is matrix element of the first medium divided by this difference of impulses, which is not 0. This causes a formation zone when this radiation formates in the first medium, and this formation zone in the second medium. You get difference between them, and just calculating this integral, you will get, for instance, if you put for matrix element just a charge of electron and something like that, and impulses for momentum is n times omega n1 times omega 1, and this n2 times omega, you are getting exactly the everything calculating. After calculating, you will get alpha. So for electron passing the interface of 2 mediums. But in this case, we are getting a neutrino. So matrix elements are different, and matrix elements given by in the medium is just photon and Z boson mixing. Electron is the electrons of the medium. So you have these four diagrams, and you are calculating these 4 diagrams. Is of course there is a Fermi constant here, and also plasma frequency, and after calculating that in standard model, everything in the standard model, you are getting this final result. It is somehow theoretical, some approximation, because exactly it is difficult to get exact answer. And so this approximate answer, you see that this part, the main part, is not depend of energy. Somehow it's also Lorentz invariant, so it is constant somehow. And this is I want to say that our numerical points, these red ones and blue one, is just this approximate solution of this transition radiation rate. So then I will move to the transition radiation in the interface of the magnetic field and vacuum, the edge of the magnetic field and the vacuum. And in this case, the matrix elements will be given by the, again, Z gamma mixing, but this loop will be in vacuum loop, exact propagation of electron in the magnetic field. So there is in that case, in magnetic field also, there is a Z gamma vertex somehow mixing, and this is not zero, it is zero only in the vacuum. And then we are getting some final answer, and final answer is the following, that this probability, this Fermi constant, alpha, and so on, this B divided magnetic field divided by B critical, and H is just some function. And this here we have this nice formula. So again, if n is bigger than 1, it seems that it is negative, but not. It is, in this case, there is an open window for Cherenkov radiation, and Cherenkov radiation I discussed with Georg Raffel many years ago in some publication. So this is a result of the probability of creating photon by neutrino at the edge of the magnetic field with the strength of the B, and this is the energy of the neutrino. So then I will move to my our last this process. This neutrino going to neutrino electron positron pairs. So you have some very dense matter. For instance, you have neutron star and so on, where a positron or electron cannot propagate. And then you go through the this neutrino can easily go through this interface, and electron positron can propagate outside, but not inside. So if again, when you compute all these two things, these two matrix elements, in the medium, it turns to be 0, because these impulses have very large imaginary parts. So this is again 0, and this is a standard model vacuum expression. And you easily calculate this, putting this vacuum. This is a matrix element, usual matrix element of the. Okay, first one is muon decay, and this is, all these things contribute to, for instance, electron neutrino scattering processes and so on. Everything within the standard model. I calculate everything in standard model, and we are getting this very nice results of order. I can show you that probability is G Fermi square multiplied by energy of neutrino to the 4 divided 2 pi to the 4 for energies much larger than electron mass. If electron mass is there, of course, there will be some logarithm and so on, and the formula is much more complex, and we cannot express them in analytical form. Probably it must be calculated numerically. So again, I want to say that this probability is Lorentz invariant. For proving that Lorentz invariant form, we wrote this more precise Lorentz invariant form, this probability from the beginning. So we have T delta functions, and I wrote this different delta functions as, for instance, in the direction of the Z. So this is the velocity of the interface. This is the four impulses of the for all particles, difference of all particles. So it is for Lorentz invariant form. This form, of course, is a Lorentz invariant. It's all these phase spaces, and numerator is the Lorentz invariant, of course, and denominator also we can write in this Lorentz invariant form. So again, in our case, this impulse doesn't conserve, so Poincare symmetry is not there, but Lorentz symmetry is there. So all our expressions are Lorentz invariant, and by using this Lorentz invariant property, we can relate to any, because we are looking to perpendicular folding neutrino to the interface. If neutrino goes to the interface by some angle, for instance theta angle, which is not perpendicular, not pi half, in that case we can relate to this probability, to the probability with neutrino energy falling perpendicular to the interface with lower momentum, lower energy. So if this lower energy with but falling perpendicular equal to energy and with some other angle. So again, it is only depend on this probability only depend on the perpendicular momentum of the incoming neutrino. So in conclusion, we can say that we discussed potentially very important processes, very important processes for a very dense environment, neutron stars or supernovas, and we discussed transition radiation for neutrino goes to neutrino photon via interaction with medium electrons, background of electrons. We take in the medium, and the transition radiation neutrino goes to neutrino to the gamma in the edge of magnetic field. In that case, vertex comes from the loops, and finally, we discussed it recently. We discussed it. Neutrino goes to directly neutrino electron-positron pairs at the interface very dense medium. So neutron stars, supernova, and vacuum. So it is the neutron. This part can be, in my understanding, can be during the collapse of supernova. For instance, you have collapse of supernova. They are flying a lot of pieces with very dense density 10 to the 10 gram per centimeter cube and higher. And then each time when the neutrino going through that, there is a probability that it will create electron-positron pairs. So, and these electron-positron pairs can potentially can contribute to afterglow this process that after explosion of neutron stars and so on we have afterglow, so this radiation and so on. I think, and I am trying to explain these things via these processes. Okay, thank you.
Thank you very much, Narine and Ara. Then, are there questions for them? I don't see any question. Then I think we should move on to the next speaker, but let's thank, yes. Okay, great. So now we have 10 minutes break. And let's thank the speaker again.